Okay, so you're being recorded, and what we're going to do is we're going to get a PowerPoint slide set up on board, and I need your help to know whether or not you can see it. Right. Now I'm hoping that everybody can see this.
Yeah, I can see it.
Yeah, we can see it.
Okay, good deal.
Yeah, I can see it.
All right, so I'm going to use the full screen so that I can manipulate the slides. Okay, so this is the first section of chapter 11, and we're going to get into ideas that go along with probability. Go ahead.
Oh no, sorry. No, you. Sorry.
Okay, so we can sort of look at probability in a number of different ways, but one of them is an empirical way, and another is a theoretical way. Now, empirical is we're using actually real data, and we're using the tools of probability, but empirical data doesn't always follow what you would think theoretical probability would be. So we'll get into that today. Okay, so some of the things that we want to understand today, we'll get into a little bit of history and how maybe some probability was used to understand science or nature that goes along with biology, for example. All right, we'll try to understand the use of probability in real world situations. Okay, let me go back here. All right, so everybody is back on board here. There is a law that goes along with large numbers. And so we'll get into that a little bit, talk a little bit about theoretical probability, and here we go. All right, so believe it or not, probability is probably one of those things that you can find in every discipline in use these days. Okay, medicine, insurance is all built around probability. Genetics is a big discipline where probability falls in. Weather forecasting, all those things are got at its core the sense of probability. All right. So it has a pretty good history that goes along with it. Many different scientists, mathematicians have been using it a long time, and everybody is around the world is using the foundation from these people here that brought it to our attention. All right, so let's get a little bit of a set of definitions here. that gives us some way of talking about probability. So we think about a probability situation when we're, operating under experiments. So a scientific method is sort of under the operation of an experiment. And we have certain results that come from that probability, and they're called outcomes, right? So this is a use of probability in experiments, and then the outcomes represent the results of the experiment. And within that experiment, or within that scope of interest, we might have different events that go along with the possible outcomes in an experiment. So an event is sort of a trial, and we want to apply some of the issues of probability to that event. Okay, so this is an attempt to give you a sense of empirical probability, and these are events and outcomes that are actually observations, okay? So we're using data, and the data are coming from an experiment, and we want to start to think about how the probability of these events could impact an experimental science-like experiment. And then there's theoretical probability, which is sort of a study of possible outcomes that might occur or should occur in a certain experiment. So we have the observations, and then we have sort of a sense of what the probability should be. And sometimes the actual observations follow those theoretical probabilities. Sometimes they are not yet following it. So here's a very easy type of equation. It shouldn't have too much impact on this, but P in this particular case, okay, P right here is the sort of the probability, and E is the event. So the probability of an event is the number of times the event occurs over the total number of times that the outcome should be. So it is a probability, and we think about this as a relative frequency. So understanding the relative frequency of an event occurring. Questions so far? All right, so let's think about this. So how about we had a quarter, okay, and we started flipping the coin, the quarter, and we flipped it 100 times. What would be the theoretical probability for this, for heads? What do you think?
Do you want the answer, or you want the formula?
Okay, what, tell me, if you were not thinking too hard about it, but how many times, if you had 100 flips, how many times would you see heads in your intuition? 50 times?
Yeah, probably about 50.
Okay, if it's a fair coin, right? So in this particular case, all right, this example right here, 44 landed heads. And what we want to do is we want to determine the empirical probability for this experiment here. All right, so 44 heads is a empirical probability. We actually did the 100 tosses, and we got heads 44 times. So if we wanted to know what the probability of that empirical experiment, we would have the number of events, 44 over 100, and that would be a probability of 0.44. Now the math is very easy there, and it shouldn't surprise you at all, but it does give you a sense of what a probability of value might be, right? So a probability here is 0.44. So that's the relative probability, or the relative frequency is 44, and we take that over 100, and the probability is 0.44. So this is an example coming from your textbook. I highly recommend that you read the textbook on chapter 11 for this. But this is a pharmaceutical company, and it's testing a drug that is hopefully reducing high blood pressure. So there are 500 individuals in the experiment, and they're taking this drug. All right. So we want to know what the person's probability of reducing the blood pressure, no change, or even increasing the probability, right? Okay, or increasing the blood pressure. All right, and so if we went into this particular situation, let's take the first one. What would be the probability that the blood pressure is reduced?
It'd be 75.8%.
Okay, and Jason, I'm thinking you're talking with me. Okay,
Yes.
and how did you get that percent?
So what you go ahead and do, you're going to do 379, which is the number of events, divided by 500. And if you do that, you'll just get the percent.
Okay, you obviously
And
you have
maybe
to
decimal form.
Right. Okay, so you can think about probability as a percent, and that's okay. But actually, the probability is a decimal point, and it has two limits. Probability has two limits. That is a probability of 0 and a probability of 1. Okay. So, for example, the probability that the sun won't rise in the day, that has a 0 probability. Okay. Right. And for example, you might think of the probability that it will rain in Florida during the summertime. Well, that's a probability of 1. So those two extremes explain what probability is. And you're right on going with 379 over 500. And of course, you would do the same thing for B, which is unchanged. And the same thing here, 59 over 500 will give us a probability of around 10% or 0.1. So here are the solutions. And those are different probabilities. Questions about that? All right. So Gregor Mendel, okay. Mendel in the 1800s, he developed the laws of heredity and crossbreeding different types of pure pea plants, okay? So he was looking at, observing relative frequencies and starting to use offspring to develop his laws of genetics. And this is a sort of a diagram that explains a part of his ideas. So he was working with pea plants, all right? And he understood that he had different colors of these pea plants. And we'll take this first situation where we have yellow and green are the pure part of the plant, and when we crossbreed these two, we got a yellow plant, right? And so in his eyes, he looked at it as a pure. And if he mixed a pure yellow to a pure green, he got yellow. Now think about this for a second. And in his mind, what do you think he was thinking? Did he get another yellow? Or would he think about this in different ways? And again, we could apply the same sort of thing for pea plants that are round or wrinkled. And he saw that as being round after one generation. And again, he had to understand this without knowledge of heredity. And of course, if you were to start a second generation of offspring, you might get a mix of yellow and green in that second generation, or we might get a mix of round and wrinkled in a second generation offspring. So Mendel came up with these ideas of dominant and recessive characteristics, yellow being dominant and green being recessive, or the round being dominant and the wrinkled would be recessive. And here is a empirical probability of genetics here. Now we have the first generation offspring, and these are two yellow or two brown from the first offspring. And after the second generation offspring. He noticed that about 75% of the second offspring were yellow, and 25% of them were green. And this was seen in the yellow and in the round sort of scenario here. Okay, so 3 out of 4 were yellow, and 3 out of 4 were round. Okay, so if we were to start thinking about this in a table form, we would start thinking about the number with a dominant trait, the number of a recessive trait, and if we were to start to think about how to look at these in terms of probability, you would say that 6,022 over the total of these two values right here and right here is going to give us a total of this right here. So if I get out of my way here, and this is 0.75 or 75%. Same thing for the round seeds. This is, we're adding this number right here to this number right here to give us a denominator of 7,324. And if we took this value here, this would be 0.75 in terms of probability. Questions about that? All right, so this went into a sense of ideas that brought to the table, and we were thinking about these cells that they called sex cells, and they were later said to be gametes that go along with this, and a Danish geneticist called them genes in the early 1900s. Okay, so the law of large numbers. All right, so this comes into play when we're thinking about how many people or how many individuals need to be tested for a very large trials. And you might have some indication of what's going on with the virus. And as you listen to it over a couple weeks, they got more and more tests done. And they wanted large numbers of these tests to start understanding the probability of having the viral infection. So here's this term, relative frequency again, and it's used in large numbers. So here is a table. I probably should have put it, but let's look at this way. So if we go from numbers of tosses, all right, this is the number of tosses, and if we thought of the number of tosses being 10, we would expect that 2 of them would be I'm sorry, half of them would be heads. That would be the expected. But whatever actually happened was we got four heads. All right, so the relative frequency here then is 0.4. And we could do this for a number of different things, 100, 1,000. For example, 1,000 again is the expected number of heads is 500. We might not get a 500, but we could get 546. And in that case, then the probability is 0.54. And if you come to this last row, you can see some variation as we go from 10 to 100,000. All right, 10 to 100,000. This is a very small number of tosses, and 100,000 would be considered a very large number. Now, the expectation is about for 100,000, the expected heads would be 50,000 right here. And in our experiment, we actually got 49,770. And that probability here is very, very close to 0.5. So as we went from 10 to 100,000, we actually started to see values that would naturally go along with the expectation. The larger the numbers that we have, the more the likelihood of hitting the expectation would be getting greater. Questions about that? Okay. So I put this up here. This is a platform that you might see in your future at Towson. StatKey is what we're using in the statistics course at Towson. And so we can use this platform, this free platform for statistics is maybe useful here. Okay. This concept, okay, of randomness, okay, the concept of randomness, which is very, very instrumental in terms of statistics, the idea of an outcome being equally likely to happen like as any other outcome could be. So if you had an experiment and you were taking, for example, slips from a hat that you said, or let's look at the lottery that we see where we have ping balls jumping around a shaker. Each one of those slips of paper or ping pong balls would be equally likely to be selected. And so if we have equally likely outcomes, then we have a true randomness in our experiment. And randomness is a very, very important part of an experiment. All right, so the theoretical probability and its equation here is no different really from the empirical probability. It's the number of outcomes favorable to the event over the total number of possibilities, total number of possible outcomes. Questions about these things? Everybody have a good sense of what the law of large numbers are? Any questions about equally likely chance of being selected? Okay. All right, so let's start thinking about a couple things here. Example number 3 out of your textbook goes into theoretical probability a little bit. Okay, so if we have a fair die and we're rolling that, that die, what would be the probability of getting a 2, for example? Now, for those people that may not understand what a fair die is, this is a cube, all right? And a cube has 6 different faces to it. 1 through 6 is on each one of the faces of that cube. So we have, what is the probability of rolling a 2? What is the probability of rolling a even number? How about a number that's greater than 3? What do you think about a number of 7? And could we say a number less than 7? So what's the probability that the die will be a 2 if you roll it once? What do you think? Well, 2, right, is one of the faces that is on the cube. And if we rolled a 2, how many what are the possibilities that go along with that? How many possibilities are there?
I would say that since the die has 6, it has 1, 2, 3, 2, 3, 6. I would say 6 times.
Okay, and let's think about that a little bit more. Okay, am I talking to Lindsay?
Leslie.
Yes? Excuse me?
Leslie, it's Leslie.
Leslie, excuse me.
No,
Okay.
you're fine.
Leslie, okay, so tell me, when you're looking at that die, does every one of the faces have an equally likely chance of being rolled?
Yes.
Okay? And so that probability, each face has the same probability of being rolled. Isn't that right?
That's correct.
Okay, and so 2 over 6 is
3.
no. I'm sorry. It would be 3, but if you rolled a 2, that would be 1 over 6.
6.
Okay. Okay, so we have a number, all right? Now this isn't 2, this is not the 2 that goes along with this. The 2 is one of the faces of the possibilities, okay? So here is the probability. That would be 0.1678, or 1/6. All right, 1/6 is 0.1678.
Now, is that a number that we'd round up?
No, that wouldn't be a number that you round up. Probably it's not 8. It's probably, let's put aside the 8 here. 1.67 is probably the rounding up. Okay. Okay, so what is an even number? What is the probability of rolling an even number?
That would be 50%.
Okay, so we have 3 different possibilities of even numbers. So those face numbers, okay, are 3, and we're going to divide that by 6, and that would be 1/2 or 0.5. All right, so what is the next one here? A number that is greater than 3.
So that would be 4, 5, and 6.
Yep, okay. 3 of the faces fall into that category. All right, and that would then be 0.5 again. Okay, so what is the probability of rolling a 7?
0.
0.
0, yeah.
Everybody knows that, right? Because it's an impossible number. It's not there. So the probability would be 0. How about a number that is lesser than 7? What is the probability of that?
All of
100%.
100%.
Okay, 100%. Okay, so the probability would be 1, right? All right. Any questions with this? All right. So here is sort of a synopsis of what we've been saying for the last half hour. Okay, so we can have an event probability that cannot occur is 0. Okay, probability that an event must be 1, that could happen too. So we know that the probability is from 0 to 1 inclusive. That is where we can include 0 and we can include 1. All right, and so if we had a sum of different probabilities in an experiment, that sum of probabilities should then add up to 1. And let me go ahead and I'm going to go back here and go to my experiment here. All right. All right. So remember this example right here? We had three different outcomes, all right? Three different outcomes: reduced, unchanged, or increased. That is reference to the blood pressure. Now, if we went to these numbers and got these three solutions, tell me if we were to sum up these three values, these three different probabilities, what is that going to add up to?
We add in all of them together.
Adding them all together, that's right. What is that? It's got to add up to
1.
1.
Yes.
Okay. So that's what this last one means. Okay. So let me go back where we left off. Okay. So the sum of probabilities equals 1. We could have a probability of event A plus the probability of not event A, and that would add up to 1. And if we wanted to sort of thinking about what the probability of not A is, that is equal to 1 minus the probability of A. All right. So here is another example out of the book. All right. And I want some help here. So think about this, this table. This table has the names of 9 birds and their food preferences. So there are 5 different types of birds. All right, so we put those names on a slip of paper, and the 9 slips are placed in a bag. All right, so we want to now determine the probability of selecting that slip. All right, so every one of these has a equal likely chance of being selected, all right? So what is the probability of a finch?
Uh, 22.2%.
Okay, and how'd you get that?
Because there's 9 different birds and there's only 2 finches, so you do 2 divided by 9, and then you get 20 or 0.222, and then a whole bunch of other 2s. So if you just narrow that down, it just goes to 22.2.
Okay, I got it. And that's a percent, right?
Yep.
Yep, okay. And so just to be clear here, this one here is a finch, this one here is a finch, all right? And that's what we're doing. We're taking those 2 and we're dividing it by the total number of the list of birds. All right, all right. A bird that has a high attractiveness to cracked corn. What do you think?
11%.
Okay, and what are you doing there? with
Pretty
your-
much the same thing as last time. So you're gonna
Yep.
so there's only one bird that has a high attractiveness to crack corn.
right?
So then there's 9 birds. You're gonna do 1 divided by 9, and you're gonna get 0.1111. And if you just narrow or simplify that and convert it to a percent, that's gonna be 11%.
Okay, that's good.
11.1.
Yep, you're doing great. All right, so how about this here? A bird that has low attractiveness to peanut kernels and low attractiveness to cracked corn and a high attractiveness for black striped sunflower seeds.
So for this question, it's not gonna be out of 9, right?
Okay, so what we're doing is we're actually going to do that. We're going to actually do it for each one of the categories. So we start with peanut, right? And how many of those are in there? Okay, 1, 2, 3, 4, 5, right? Okay, and then we come over here, we take those 5 and we start to apply that to the next thing, which would be low attractiveness. I'm sorry, for cracked corn. So that would be this one.
5.
Yep, this one here. All right. And this one here and here, right? And then this one here and here. Does everybody sort of see that?
Yeah.
Yeah, I see it.
Okay, and then you add on the last one, all right? High attractiveness to the sunflower seeds. And that then is this here, here, and here. So that would be 3 out of 9. Okay, follows that particular outcome. Everybody see that? So that's going to be 3.
0.33.
Yep, that's right. Okay. Questions? Okay. So a bird that has minimum attractiveness for peanut kernels or cracked corn.
Would that be 66%?
Okay, 66%. Let's find out. So here are the ideas, and write down in here, 6 of the birds are having that sort of understanding. And so this would be 6 over 9 or 0.667. I think that's what you said.
Yeah, pretty much.
Okay. Questions about this? Okay, how about a deck of cards? Everybody know what a deck of cards are? All right, let's just think about it real quickly here. We have a deck of cards. The total number of cards are 52 playing cards. All right, there are numbers and face cards, okay, from 1 through 10, J, Q, and K is the Jack, the Queen, and the King. And then we have 4 different suits: hearts, clubs, diamonds, and spades. Okay, so 13 across the rows, and 4, I'm sorry, 13 over the columns and 4 on the rows. All right, 4 times 13 is 52. All right, so each card, right, each card has an equally likely chance of being selected. Is that true?
Yes.
Yeah.
Okay, and if you said, well, what is the probability of selecting any one of those cards?
It'd be about 1.9%.
Okay, 1.9%. And what you did, Jason, I think, is that you took 1 and put it over 52 to get that number.
Yeah.
Okay, so every card has an equally likely chance of being selected. All right, so this is a bigger look at it just so that you can see it. Does everybody understand what playing cards are? Okay, so let's think about this. Here's an explanation about the cards. Okay, 13 cards. And then we have 4 suits that go along with that. And we have a color that comes in too. So the hearts and diamonds in terms of suits are red, and the spades and the clubs are black. All right. So we say, okay, what is the probability of drawing a 8?
It'd be 7.6%.
Okay. I got 7.69.
Yeah, I kind of just cut it off after the 6, but
Okay.
yeah, I'll just remember to keep it there.
I
Well,
got
I would,
7.69.
yeah.
Yeah.
I would use, if you're going to use decimal places, I would use at least 3, and in that case, it would be 0.077. Okay, so Jason, a round up there.
Okay.
Okay, so here's the other one. Okay, then how do we get to a card that is not an 8? What would we do to think about that?
So you'd subtract 4 from 52 because there is 4 8s. And then
Yep.
you would go ahead, that equal 48, and then you do 48 divided by 52. And with that, you'd get 92.307.
Right.
Okay, so I've got my calculator here, and I heard what you were saying, and you're right on the mark, and your answer is correct. But there's one way that we can sort of think about this, or another way that we can think about this, right? We know that the probability of all the cards, picking all of the cards, is going to be 1, right?
Yes.
And now we can say 1 minus the answer that we had for the 8, okay? So 1 minus, sorry, 1 minus the answer that we got here. Isn't that right? So if we had 0.077, we could go 1 minus 0.077 to get the same answer that you got, Jason. Is that true?
Yep.
Okay, that's good. All right. So what is the probability of drawing a club?
A club, that'd be 25%.
Okay, 13 cards in a deck, right? Have are clubs. So 13 over 52 would be 0.25.
Mhm.
Questions about that? Okay. So what is the probability of selecting a jack or a queen or a king? So those are the three what are called face cards or picture cards.
I got 0.23.
Okay, and what are you? How are you doing that, Leslie?
I had because they have 4 jacks, 4 queens, and 4 kings. I added all of them together, which was 12 divided by 52.
That's right. Okay, so so here I'm going to try to get you to think about this. We could say that or is a situation where we can put a plus sign over, right? A plus sign over this. So we could take the probability of a jack and we're going to add the probability of a queen, and we're going to add to that a probability of a king. All right? And that's what we could do here to get that idea going. Okay, so what is a heart and a spade?
That'd be 50%.
Okay. Now I'm gonna drop back here. Can we have a situation where there is a heart and a spade too?
Like, can you say that again?
Do we have a card that has a heart and a spade on it?
Not, I don't think so, no.
Okay.
I can't see it, so
So the probability is what?
Oh, so a heart and a spade at the same time.
Yep.
Okay. So that'd be 0.
Okay. All right. All right. Okay. So let's go ahead and think about this. Okay, so we got the probability of this one here is 0.077. Not an 8. That would be minus 1 minus that, and that would be 0.923. A club is 13 cards in a deck, so that's 13 over 52. All right. And Jack or a queen or a king is 12 picture cards, and that's 12 over 52, which will be 0.231. Okay. Okay, the word "and" means both events occur at the same time, and a heart and a spade cannot be one of those cards, so that's a probability of 0. And we can start to think about the greater than 4, and I'm sorry, the greater than 5 and less than 4. That would be 6, 7, and 8. And that would be, again, 3 different cards. And that would be 12 cards over 52. Questions about that? All right, so that is the last slide. All right, and I see that I have a larger audience here. All right, so we're going to turn the recording off, and